people, last video for the factoring. Let's go ahead and jump right in. Okay, let's consider 0.04 x squared plus 0.28 x plus 0.49. Okay. Again, we're dealing with decimals. Again, those decimals can be changed into fractions. And again, okay, here's the thing. You need to be able to deal with fractions, okay? But if you don't have to, why would you want to? Okay? When all you really have to do is just factor out a 1/100th, and then you have whole number, or integer, whatever you want to call it, coefficients. And at this point, we see a perfect square here. We see a perfect square here. We want to know whether this is 2 times 2 times 7. It is. And this actually winds up being 2x plus 7 quantity squared. Okay. Now, you could have done it with the decimals or with the fractions still in it. But here's the thing. Numerical factors have nothing to do with solutions, right? So why not figure out how to make it easier on yourselves up front, right? This is one of those stop, think, then do kind of moments, okay? Let's move on. We have 3x to the 5th minus 12x squared. And you're like, well, that's a fifth. That's neither a square nor a cube. And it's a difference, but that's a square. And man, they don't match. What is going on here? And then you think to yourself, I remember something that Mr. Forth talked about in terms of GCF being the first thing I need to look for, and it being the easiest factoring to do and the easiest to forget. So let's not forget it. Okay? And then you get to here, and you want to keep going, but in terms of official factorization, you're actually finished. Okay? Because that's a cube, that's a square. It's not going to factor any further. Now, let's go ahead and let's do another one. How about, let's see, 2y to the 4th plus 5y cubed minus 12y squared. Okay. And again, you're like, well, is that quasi-quadratic? I mean, it kind of looks like it. Actually, no, it's not quasi-quadratic. It's actually quadratic the moment that you take the GCF out. Okay. And the moment that you take the GCF out, all of a sudden, this is a pretty easy one, right? You know that if it factors, and by the way, it does, if it factors, since 2 is prime, it has to break apart into 2y and y. The only problem is this 12 right here, and whether 12 breaks apart into 1 and 12, 2 and 6, or 3 and 4. Now, it's probably not going to break apart into 1 and 12 or 2 and 6. Those factor pairs, each one of the pairs is far enough apart where it would probably cause a difference between the products larger than 5. It's within the realm of possibility, especially 2 and 6. But since this is relatively small, 5, and I know that one's going to be positive and one's going to be negative, let's go ahead and entertain the possibility that it's 3 and 4. And if I have 3 and 4, I can have 8 and negative 3, and that's going to give me positive 5 for a middle term. Okay. Let's go ahead and do a couple of more. Let's just do x cubed over 1/8. Now, you don't have fractions all the way through here. But you can, basically here's the thing. This is equal to x cubed minus 1/2 cubed. But if you're more comfortable, you could factor a 1/8 out and have 8x cubed minus 1. Right? Because remember that when you factor, you're unmultiplying, you're dividing, right? And when you divide by 1/8, as you would in both terms, dividing 1/8 by 1/8 obviously gives you 1, but dividing 1 by 1/8, dividing by 1/8 is the same as multiplying by 8. And so you get this, and so for some people, they just want to get rid of the fraction and pull it out. And then, of course, what's being cubed here in this first term is 2x. And so it becomes 2x minus 1, and then 2x squared plus 2x times 1 plus 1. And that is your factorization. Now, if you chose to do it this way instead, you would simply get x minus 1/2, and then x squared plus 1/2 x plus 1/4. And here's the thing, that is exactly the same thing. If you were to take 1/2 of this and multiply it by this and take the remaining 1/4 and multiply it by this, this is what you would get. But here's the thing, if you want to relieve yourselves of the burden of dealing with the fractions up front, then basically factor out all of the denominators, or so that all you're left with is integer coefficients, and that winds up being, kind of cool, right? That's a way of basically taking the fractional aspect out of the problem, such that you don't have to deal with it anymore. Let's deal with another example. Now, right here, you're thinking to yourself, this could be a perfect square trinomial, and it is, okay? Because this right here is 1/2 x, this right here is 5 squared, and this middle term is 2 times 1/2 times 5 times x, right? And then 2 and the 1/2 cancel out. But let's pretend that we don't see that yet, and I want to get rid of that 1/4. Well, all I have to do is pull out the 1/4, and when I factor a 1/4 out, that's functionally the same as multiplying all of the terms by 4, right? Because to divide by 1/4 is to multiply by 4. Now the perfect square nature of this trinomial is much more evident, and I know that it's x minus 10 squared. Now, if you had just done it from here, it simply would have come out as 1/2 x minus 5 squared, which of course, when I set x minus 10 equal to 0, when I set 1/2 x minus 5 equal to 0, I get the same thing. Either way, I get x is equal to 10, because remember, numerical factors do not impact zeros, okay? Let's do one more, and this is kind of a nasty one, but nasty in the best possible way. Okay, let's say we have something like p plus 3 minus 3 minus p cubed. Now, there are about 3 ways to do this. First of all, let's look at, let's say I don't want to get involved with the fact that that's the difference of 2 cubes, but each one of the cubes is a binomial, and the thought of keeping track of all that is making my head hurt, okay? Well, would it work if you multiplied it all out? Could you then see the factorization? And the answer is yes, okay? Now, for those of you who do not remember your binomial theorem or Pascal's triangle, when you expand a binomial cubed, the coefficients wind up being 1, 3, 3, 1, okay? So let's expand this p plus 3 cubed, and you wind up with p cubed plus 3p squared times 3 plus 3p times 3 squared plus 3 cubed. Now, I could take that negative and use it to flip that thing around, right? Because 3 minus p to the third is the same thing as p minus 3 to the third times a negative 1. And so you could factor out a negative 1 out of here, but really you're factoring out a negative 1 cubed. But a negative 1 cubed is negative 1, right? But let's pretend that we don't see that, and you want to expand it. Well, it expands the same way, and you get 3 cubed, right? And let's talk about this as plus a negative p. That makes it a little bit easier. So I have plus 3 times negative p. So that's 3 squared times negative p, plus 3 times negative p squared plus negative p cubed. And then I have to clean it all up. Whew. Okay, p cubed plus 9p squared plus 27p plus 27. And we'll go ahead and not distribute the negative just yet. I don't want to lose negatives when I'm trying to simplify this negative p to various powers. Yeah, minus 27 minus 27p plus 9p squared minus p cubed. Okay. Now, let's go ahead and distribute. Let's take that negative and use it to change all of those signs. And what you get here is this 27 and this negative 27 cancel out. This 9p squared and this negative 9p squared cancel out. And what you're left with is 2p cubed plus 54p, which if you pull out a 2p, you're left with p squared plus 27. And there's the factorization. If you were to do it by the difference of 2 cubes, you wind up getting the same thing. Okay. You just have to remember that that is a single quantity, that is a single quantity in terms of basically this is our A and this is our B for our formula, okay? So what we have here is A minus B and then A squared, okay, plus A times B plus B squared. Now here's the thing. If I were to actually flip this around to 3 plus p, I notice that those are conjugates of each other, and I'm going to get the difference of 2 squares. Now remember, this is squared, so I can actually flip this around as p minus 3 squared, and that's just a little bit easier because we tend to think a little bit better when the variable comes first. Now over here, once I distribute this negative, the 3's are going to cancel out, and I'm just left with 2p. That 2p? Yes, that 2p. Now this, when I expand it out, is p squared plus 6p plus 9. This right here is 9 minus p squared, and this is p squared minus 6p plus 9. Whew. All right, 6p, negative 6p, cancel out. Negative p squared, positive p squared, cancel out. And all I'm left with here is a p squared and 3 9's. So it's 2p, p squared plus 27, and that is exactly what I got above. Okay? Again, I'm trying to basically go with some of the more challenging problems, especially ones that are going to incorporate several elements within the working of the problem itself. That gives us a better idea of, that gives us, more advanced practice in terms of factorization being part of a larger problem, okay? This is pretty much it for the factorization techniques and procedures. We're going to go ahead and there will be videos on rules of exponents and properties of logarithms, and of course problems on z problems. All of those together with the trig stuff, unit circle values and trig IDs, will form the basis of your cumulative quizzes, at least for the first part of the year. Okay. Again, if you have any questions, shoot me an email. Bye.